This is day 23 of coding every day until I hit 1K subs. Today, I focused entirely on LeetCode, tackling a mix of problems. Let's dive in. Alright, let's jump into the LeetCode problems I tackled today. First up was problem 416, Partition Equal Subset Sum. Spoiler alert, the goal here is to see if you can split an array into two groups with the exact same sum. Okay, here's the code. The main idea is dynamic programming, sort of like a variation of the knapsack problem. First, if the total sum of the numbers is odd, it's impossible to split them into two equal halves, so we immediately return false. Otherwise, we calculate the target sum, which is just half the total. Then, we use a set to keep track of all the possible sums we can create using the numbers we've encountered so far. Starting with 0, representing an empty subset, we iterate through each number in the input. For each number, we figure out what new sums we can make by adding this number to the sums we've already found. If we ever manage to create a sum that equals our target, we've succeeded and can return true. If we go through all the numbers and never hit the target, we return false. This approach efficiently explores possible subset sums. Next, I tackled problem 368, Largest Divisible Subset. Another spoiler warning. This one asks for the biggest subset, where for every pair of numbers in the subset, one number divides the other evenly. So for this one, the crucial first step is to sort the input array. Once it's sorted, this problem feels very similar to finding the longest increasing subsequence. But instead of checking if a number is greater, we check if it's divisible by the previous one. We use dynamic programming. We maintain an array, let's call it dp, where dp at index I stores the size of the largest divisible subset ending with the number nums at index I. We also need another array, parent, to remember which number came before nums at index I in that specific largest subset. We iterate through the sorted numbers, and for each number we check all the numbers before it. If the current number is divisible by a previous number, we see if we can extend the subset ending at that previous number to make a larger subset ending here. After filling the dp and parent arrays, we find the index that corresponds to the overall largest subset size. Then, we use the parent array to backtrack and reconstruct the actual subset elements. The time complexity ends up being about n squared because of those nested loops after the initial sort. Alright, then I did problem 1863, Sum of all subset XOR totals. This asks for the sum of the XOR values of all possible subsets of the input array. Here's the surprisingly concise solution I ended up with. There's a really neat mathematical or bitwise trick here. It turns out that if a specific bit position, like the 1's place, the 2's place, the 4's place, etc., minus is, or set to 1, in any of the numbers in the input array, then that same bit will be in the final XOR sum for exactly half of all possible subsets. So the strategy is, first, figure out which bits are set in at least one number. We can do this easily by just doing a bitwise OR operation across all the numbers in the input array. This gives us a single number where a bit is set if and only if it was set in any of the original numbers. Then we take this combined OR result and multiply it by 2 raised to the power of n-1, where n is the number of elements in the array. Multiplying by 2 to the power of n1 is the same as shifting the bits left by n-1 positions. This multiplication effectively accounts for that half of the subset's contribution for each bit that was set in the combined OR value. It's a pretty clever shortcut compared to actually generating all subsets and XORing them. Finally, I solved problem 1123, lowest common ancestor of deepest leaves. The goal here is to find a specific node in a binary tree. We need the node that is the lowest common ancestor of all the leaves that are at the maximum depth in the tree. Here's the recursive approach using depth-first search, which works quite nicely. The core idea is to design a helper DFS function that returns two pieces of information for any given node. First, the depth of the deepest leaf found in the subtree starting at that node. And second, the actual lowest common ancestor node for those deepest leaves within that subtree. When we call this function on a node, it recursively calls itself on the left and right children. If the left child's subtree contains deeper leaves than the right's, then the deepest leaves overall for the current node are the ones in the left subtree, so we return the left's depth, plus 1 for the current level, and the LCA we got from the left side. Symmetrically, if the right is deeper, we use the right's results. The interesting case is when the maximum depth found in the left subtree is equal to the maximum depth found in the right subtree. This means the deepest leaves are spread across both sides, making the current node the lowest common ancestor for all of them. In this case, we return the shared depth, plus 1, and the current node itself. Calling this DFS function starting from the root of the whole tree gives us the final answer. We just need the second part of the return tuple, which is the LCA node. And that wraps up day 23. 4 LeetCode problems today. Felt pretty productive covering different dynamic programming ideas and tree traversal. If you enjoyed this or found it helpful, please give it a like, subscribe if you haven't already, and maybe drop a comment with your thoughts, or maybe if you have a different approach to one of these problems. Any support helps the channel grow, and you can also support the channel over at buymeaboba.com, link in the description. Thanks for watching, and I'll see you tomorrow for day 24.